Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're focusing on chapter 11, oxygen distribution in rivers and lakes. And today we'll be closing off our review of this chapter with the summary in subchapter 6. So let's get started. Dissolved oxygen is essential to the respiratory metabolism of most aquatic organisms, the ecosystem functioning of freshwaters, and the ecological quality of lakes and rivers. In addition to altering organism habitat, oxygen distributions are important for the metabolism of many organisms and affect many biogeochemical cycles, as well as the productivity of aquatic ecosystems. Low oxygen levels are generally associated with poor water quality and degraded habitat for organisms. The solubility of oxygen in water decreases as temperature increases. The solubility of oxygen decreases with lower atmospheric pressures at higher elevation and increases with greater hydrostatic pressures at depth within lakes. Oxygen solubility decreases exponentially with increases in salt content. Oxygen content is often reported as percent saturation with respect to the solubility concentration at atmospheric pressure at the surface of the water body. The variability of oxygen dynamics in inland waters results from the combination of exchanges with the atmosphere, advection, dispersion, and biota-mediated transport, photosynthesis, photorespiration, etc. Surface and subsurface water flow are of paramount importance to understanding oxygen dynamics in rivers. Lateral and vertical flow pathways are involved in the advection of dissolved oxygen as well as other substances indirectly influences riverine dissolved oxygen dynamics. While the oxygen content within small high gradient streams is usually near or above saturation due to the high turbulent mixing of water, marked variation occur spatially and temporally in low gradient streams and rivers and are often coupled to variations in the discharge and loading of nutrients and organic matter. Lateral and vertical hydrologic exchanges represent a major source of dissolved oxygen variability in rivers and also affect other key substances indirectly, influencing riverine dissolved oxygen dynamics. Oxygen concentrations in rivers can vary temporally on diel, seasonal, annual, and decadal scales. This spectrum of temporal signals combines to shape the oxygen dynamics of a river, which depends on the hydrological and biogeochemical conditions of the river's catchments. Similar to rivers, oxygen concentration in lakes vary both temporally on diel, seasonal, and annual scales, and spatially on horizontal gradients between littoral to pelagic sites and vertical gradients with depth. On an annual scale, dimictic north temperate lakes exhibit 4 distinct oxygen vertical profiles: orthograde, clinograde, positive heterograde, and negative heterogrades. These oxygen profiles are determined by a lake's productivity, mixing regimes, and climate, as well as shorter-term factors influencing the development of metalimnetic oxygen maxima and minima. Examining dissolved oxygen profiles in lakes with amictic, warm monomictic, dimictic, cold monomictic, polymictic, meromictic, and oligomictic mixing regimes provides insights into the substantial variability in dissolved oxygen dynamics that lakes can exhibit. In general, the many lakes with clinograde oxygen profiles exhibit greater variability in dissolved oxygen dynamics during thermally stratified periods than the few lakes showing orthograde oxygen profiles. Lakes globally are exhibiting decreased oxygen concentration in both their surface and bottom waters due to climate change and land use change. Ultimately, clinograde oxygen profiles in lakes will likely become more frequent due to global change, resulting in long-term changes to lake ecosystem functioning. Anoxia and hypoxia are among the most acute environmental problems facing inland waters, as their prevalence has rapidly increased and likely will become even more frequent in the future. Metrics to assess anoxic and hypoxic conditions are based on oxygen concentration, on the calculation of rates of oxygen consumption in the hypolimnion, and on the estimation of the temporal and spatial extent of anoxia in lakes and running waters. Annual anoxia extent in lakes can be predicted using regression-based models with variables related to lake morphometry, hydrology, and trophic states as predictors. In reservoirs, variables related to hydrology and organic carbon load from tributaries work better. Dynamical process-based models are used to predict oxygen deficits at smaller time steps, for example daily, and the inclusion of the multifaceted processes affecting oxygen concentration makes them useful tools to assess the impact of climate change on oxygen deficit in inland waters. Anticipating climate change impacts on oxygen deficit in inland waters is challenging because shifts in climate will be accompanied by changes in many other aspects influencing oxygen concentrations. Impacts of climate change on oxygen solubility, stratification, respiration rates, stream flow, nutrient points, and diffusive sources and extreme weather events will shape the future prevalence of oxygen deficit in inland waters. And that's it for Chapter 11, Oxygen Distribution in Rivers and Lakes. And tomorrow we'll be tackling on a new chapter, which is going to be Chapter 12. And let's look at the title of that chapter so that I excite you with this new program here. And we'll be looking at salinity and ionic composition of inland water with Hilary A. Duggan with the Center of Limnology at the University of Wisconsin in Madison, Wisconsin, in the US. And this is the outline. So I'll talk to you tomorrow, and thanks for attending today's short summary on oxygen distribution in lakes and rivers. Talk to you soon. Bye.